Hey, good afternoon. So today we'll continue on uniprocessor scheduling, and hopefully I get a chance to talk about multiprocessor or start multiprocessor scheduling today. We'll see. Okay, so let me just check one thing real quick. Yeah, okay. So where we left off last lecture was basically talking about fairness. So the starting point was a strict priority scheduling, which is the scheduling policy that you guys are going to implement in Lab 2. By the way, Lab 2 will be released tonight. Fingers crossed. We're just in the last steps of adding test cases. So this is the first year out of the 3 or 4 years that the first term out of the 4 terms that I'm teaching this, that we're releasing test cases. So this is the feedback I got from the previous terms, that people wanted test cases. So that's why we're adding test cases. Now the test cases that we're releasing need a little bit of ironing, so that's probably ends tonight. The manual has been ready for quite a while now, but anyhow, so hopefully tonight it will be released, and there you're going to implement a strict priority scheduling. And as we talked, it kind of starves the low priority threads, because as long as we have high priority threads, we're going to run them. An alternative to that is multi-level feedback queue. Now, the idea here is to have queues with different priorities, but then move threads between these queues. Do not keep them in high priority queues. So one way to do this is this multi-level feedback queue. Now in this one, we have a bunch of queues. The higher priority queue, let's say, is the top one, and the low priority queue is the bottom one. Now we run round robin on higher priority ones. This is one example. You could potentially run other, like you can do other types of scheduling, but the multi-feedback queue runs round robin. Now, the higher your priority is, the shorter the time quantum is going to be. Once the time quantum expires, we're going to move the task in that queue to the next queue, and where the time quantum increases. Now, the last queue in the list, there might be more than 2 or 3, right? The last one is just FCFS, which means that the time quantum is kind of infinity, right? If you remember round robin, with infinite time quantum becomes FCFS. Now, why is this a good design? So this is a good design because it kind of is a good trade-off between fairness and response time. If you remember from the previous, like it was the last thing in the previous slide, or previous slides, when we talked, I don't exactly remember where it was, but one of the things that we said was there is always this trade-off between performance and fairness, or sorry, response time and fairness. Now this one, yeah, this is slide. So it seems like there is always this, if you want super fairness, then you're gonna have bad response time, and if you want really good response time, then you're likely to have really bad fairness. Now this one is something in between. Now, why is this good for response time? Let's say your task is a short task, So for response time, you want to get short tasks executed first. If you remember, the best scheduling policy when it comes to average response time was shortest task first. So if you can execute short tasks and give them priority, it's going to be really good for your response time. And this one does so, right? Because if you have a short task, your task is going to go to this first queue, and it's going to get really short time quantum. But if it is a short task, it's going to be done. So we're going to be done with this task immediately. Now, if you have longer tasks, they're going to get some shot at the CPU first, then they're going to be moved to the second level, and then the third level, fourth level, and eventually they're going to come down here, and then they're going to be executed until they complete. So we're not, if in shortest task first, if you remember, we were kind of starving the long tasks. So if you get short tasks very frequently, you're going to just be running them, and long tasks are going to get 0. In this one, if you're a long task, you get a shot here, you get a shot here, you get a shot in other levels, and eventually you finish here. So we're not unfair to you, but at the same time, if you are a short task, you have a chance to get executed right off the bat and get some high priority at the beginning and be done. So this is why this model is kind of like a middle ground between really good average response time, but also reasonable fairness. So right, so as I explained all of that, now in order for us to move between these threads, one thing that we could do is to have, as I explained previously, we could have, we can divide the time between these queues. We can say, 80% of the time I'm going to dequeue tasks from the first one. Let's say 50% of the time I'm going to dequeue tasks from the second one, and like 5% of the time I'm going to dequeue tasks from the last one. That's one thing we can do. Or we can do, strict priority. We can just, as long as I have tasks in the first one, I just execute them. Once I'm done with those, I come to the second one and I execute them. And then I go to the last one. And then here, another trade-off between what we can do. Okay. So this, as I mentioned, kind of approximates shortest remaining time first, because it prioritizes tasks with short periods, because they get to execute here and be done with, and run long-running tasks most likely will end up coming at the bottom of this, but it's also good for fairness, because the long-running tasks actually get to run on the CPU and not be starved. Now, as I said, moving between the queues, you can do fixed priority scheduling, or you can time a slice. So these are two options that you can do, as I explained in the in a few seconds ago. Now, this is an interesting story, and seems to be real, as far as I know. So this actually was implemented in MIT computers back in then. This exact scheduling policy was there. Now, so they had this game that they were playing. So like game of chess, for example, if you're playing game of chess, like in this example, they were actually playing Othello contest, but in game of Go, for example, or different games, what happens is that you don't, if let's say you look at game of chess, the game tree is really big, right? So you make a move, then your opponent makes a move, and then you make a move, and then your opponent makes a move, and so on and so forth. Eventually, the game ends, and here you win or you lose, right? But this game tree, let's say for chess, is really big, and if you want to solve this, you probably cannot expand the game tree to the bottom of it and make good decisions here at top. So usually what happens is you want to cut this, right? Let's and then look at the state here and see how good this state is. For example, give these intermediate states. These are not end states. Some score. And then make a decision here at top to say, okay, if I make this action and my opponent takes this action and so on, then I find myself in this state, and this state is not a good state, or it's a really good state. Now, where you draw this line is important, right? If you have more resources, if your computer has more memory, if your computer has more computing power, you can go deeper in this tree, and probably you get a better approximation because this is closer to the terminal state, and it's easier for you to give it a score. Now, why am I saying these things in the middle of an operating system course? Now, in MIT, they had this uniprocessor machine, and there was a contest. So different groups had different codes to, play the game, and you get to run, make a decision, and then it would go to the opponent. Your opponent would make a decision, and then you make a decision, and so on and so forth. So these are two programs playing on behalf of these two groups. Now, as I said, it's important where do you draw this line, right? The more you can expand the game tree, the more accurate your decisions would be. Now, one of the groups knew that the scheduler on the system was doing multi-level feedback queue. And at the time, if you were a task here, high priority task, let's say the time quantum was 8. Let's say you run for 6 microseconds, and then you do I/O. So if you do I/O, you're going to go to I/O, and then you're going to come back. In the multi-level feedback queue that was implemented at MIT, when you would come back, you would be put back to this list. So as a result, you don't go to the next level and get lower priority. You stay high. So, and if you stay high, you get to run on CPU more. And if your competitors keep going down on this, so they get less computing resources, they're gonna not be able to expand this tree to higher degrees. So this group was doing these printfs, like just printing one character, very smartly before the time quantum expires, so that they would just be all the time on the high level queue and get more resources. So the way to fix this is easy, right? What you could do instead of, just putting them back is to just keep a counter for each task, how long they have run at this priority level. And once they hit cumulatively 8 microseconds, then you can push them to the lower queues. But it was like this shows you that, knowing what the system does, how tasks are scheduled, how tasks are, consuming resources is important in the performance of your application. Here, somehow maliciously, some groups, misused this information in their advantage. But it's always beneficial to know how resources are consumed in your computer. Okay, I got a question. So does each queue with differing time quantum represent a separate thread within a CPU execution? the tasks within that queue. No, these are different ready queues, really, right? So your task comes to this queue. So you can think of them as ready queue 1, ready queue 2, ready queue 3. You could have like 3 ready queues, and then you're passing TCBs between these ready queues. So these are scheduler ready queues. They don't represent threads or CPUs. They're just ready queues that we're moving TCBs from and to them. Okay, now I'm going to switch gears and talk about pure fairness policies at this point. So we started with first come, first serve, then round robin, then shortest task first, then strict priority, and then multi-queue, multi-level queuing, and the 6th scheduling policy we're going to talk about is lottery scheduling. So in this one, so you have a set of tasks, and you give each task some number of tickets called lottery tickets. So task I gets NI lottery tickets. How are we going to use this? So at each time slice, so we're going to have something like a round robin. Now in round robin, I have a single queue. You get your time slice, and then I go to the next one, and then I go to the next one, and then next one, and then come back. In lottery scheduling, once the time slice is once the time quantum is done, I don't necessarily go to the next task in the queue. I run a lottery between all the tasks that are ready, and then each lottery ticket that wins, I run the thread corresponding to that lottery ticket. So now what happens? If I run this for a while and then look at the average time that each thread got to run on CPU, you would expect to see each task on average runs in proportion to the number of tickets that they have. So the more tickets you have, the higher your chances of winning the next lottery, and the higher your chance is to run on the CPU. And if we have a fair lottery, meaning that if each lottery ticket can be chosen with the same probability, then a thread that has 2 lotteries on average runs twice as much as a thread with 1 lottery, right? So this is a good way to kind of have priority over threads. So if one thread is more important than the other one, I give that thread more lottery tickets. Now, how do you want to, set priorities? How do you know which thread gets more lotteries? That depends on your system, right? So let's say if you're Amazon and you're, selling these EC2 instances, if you have an instance that people have paid more for, you can give that instance more lottery tickets. Let's say if you have an instance where the price was twice as the other one, maybe you can give that instance twice as many tickets as the other one. If you are implementing some other systems where response time is really important to you and you have some sense of how long each task is, you can give tasks ticket in proportion to the reverse execution time. So the more your execution time is, the lowest number of tickets you get. The shorter your execution time is, the more tickets you get. And so on and so forth. Now, this is good because it avoids a starvation, right? We're not going to starve because there is a chance that even if you have only 1 lottery ticket, there is still a chance that you win that lottery. That lottery ticket will win. So everybody will kind of make some progress, but the progress people are making is kind of random. And we can talk about expectation, like in expectation, on average, how much you get to run. Now, what's the downside of this? The downside is the variance. So we can talk about average, but what about variance? So hopefully you have taken some courses on probability, but whatever distribution you're looking, it has an average, but it also has a variance. The variance shows you how close people are to the variance. And in this one, if you have a single lottery, on average, you're going to get 1 over the number of lotteries time on the CPU. But that's on average. If I run this for a while, you might get 2, you might get 3, you might get nothing, right? So the variance is important. This lottery scheduling is really bad if you want to implement it in a real-time system, because everything is random and there might be some variance. All I can say is on average what happens. I can't really talk about short periods of time because there might be a lot of variance. The other thing about this is how you allocate CPU also depends on how many other tasks are in the system. Let's say I have a single lottery ticket. Now, this doesn't tell me how much time I'm going to run on the CPU, because if I'm the only thread in the system, then there's only one lottery, so I'm going to be the winner every round. If there are thousands of lottery tickets in the system, then I will get 1,000th of the CPU time. If there are 100 lottery tickets in the system, I'm going to get 1 divided by 100 time on CPU on average. So it's kind of like how much I get depends on how many other threads are in the system. So this is good again and bad, right? The good thing about it is that, you know, I can if there is a maximum number of threads, I can say, you know, worst case I'm going to get this much, but I might get even more than that, you know, if there are no other thread in the system. But the downside of it, if you have a real-time system, then you kind of don't have any control over how much CPU you're going to get, because it all depends on how many other threads are in the system. So it's good and bad depending on what you really want your system to have. So here is a example. I'm going to just run over it really fast. You know, let's say that we have 10 tickets, and we're going to give 1 ticket to long task. Now, if we look at the ratio of oh, sorry, we have 11. We have so let's assume that short tasks are getting 10 tickets and long tasks are getting 1 ticket. Now, let's look at the ratio of how many short tasks we have, how many long tasks we have. So this slide emphasizes what I said about it really depends on who else is in the system, right? So if my system has 1 short task and 1 long task, then the short task is going to get 10 divided by, it's going to get 10 divided by 11 percent of, oh my God, it's going to get 10 divided by 11% of the CPU, which is about 91%. If there is no short task and there are 2 long tasks, then, well, the short task doesn't exist, so why are we talking about it? But then the long tasks are going to get 50% because there are 2 of them and they have equal number of tickets. Each one of them has 1, so it's going to be 50-50. Now, if there are 2 short tasks then each short task is going to get 50%. Now, already you see that, you know, the percentage differs from these two. Like if I have one short task and one long task, my short task is going to get 90% of the time on the CPU. If I have two short tasks, then my short task is going to get 50%. So it really depends on who else is in the system. How much I get depends on how others are in the system, or how many other tickets there are in the system. And you can do the math for the other two. And the last point here is talking about really the variance. So right, so if you have too many short tasks, then you know, each one of them is going to get they're going to just timeshare the system between each other. And it's going to be really hard for each one of them to make progress, right? Because you have too many short tasks, and all of the short tasks have equal probability, equal priority, because all of them have the same number of tokens or the same number of lottery tickets. So, you know, you would be better off running round robin, because then it's kind of like deterministic that you're going to get certain, like, your one time quantum every n time quantum. But if you go with lottery scheduling, on average you get 1/n, but then there is variance. Sometimes you might get 2, sometimes you might get 0. So there is no guarantee of how much time you're going to get in short periods of time. Which brings us to this slide. Now, in this slide, let's define unfairness to be the finish time of thread 1 divided by the finish time of thread 2. Let's say I have 2 threads in my system, and let's say they have equal number of lottery tickets. So both threads have, let's say, 1 ticket, or both threads have 2 tickets, whatever. So they have the same number of tickets. Now, I'm interested in to see when they finish their task. When do they finish? Let's say both of them have come to the system at the same time, and let's say both of them have the same execution time. Let's say both of them take 1 minute, and let's say the time quantum is 1 second. So I'm going to run this lottery every 1 second, and I'm going to give the CPU to one of these threads. Now, one of them will finish first, and then the second one is going to finish. Now, I'm going to look at the ratio between these two, which one finished first and which one finished second. Now, this shows you this ratio unfairness on y-axis, and on the x-axis, I have the length of these jobs, the length of these 2 tasks. As you can see, if these 2 tasks are short, then one of them might finish really early, and then I go to the second one. This is where the variance comes in. They have equal number of tokens, they have equal number of lottery tickets, but there is a variance. It doesn't guarantee that in a short period of time, they both get equal number of time quanta on the CPU. So one of them could finish first, and then I can just run the second one. So it could be as bad as one of them finishes at time 5, the other one finishes at time 10. So there's a twice unfairness in this system. If, however, the length of these 2 are large, let's say, you know, they take 1 hour and my time quantum is 1 second, so I'm going to run this lottery a lot. And if I have more instances, then the variance comes down, right? If I'm looking at this at a long period of time, then my samples are going to be more accurate. So they're going to almost finish at the same time. So how fair lottery scheduling is kind of depends on how long your tasks are, because that shows how many samples I'm going to take, how many times I'm going to run this lottery. So the more I run it, the lower the variance becomes. The less I run it, the more variance I have. Now, to deal with this, to bring the variation down and still have some randomness, because this randomness is kind of good. This randomness kind of makes sure that you're not starving tasks. So everybody gets a shot if their lottery ticket wins. But the bad thing about it was this variance. So is there any way we can keep this randomness and this proportional allocation, but also bring down the variance? And the answer to that is yes, and that's a stride scheduling. How does this work? So we still want to have this randomness, and we still want to allocate the CPU to different threads based on the number of tokens that they have, or the number of lottery tickets that they have. How do we do this? We define a stride for each thread. So a stride is basically a big number W, divided by the number of tokens that, or by the number of lottery tickets that each person has. So here's an example. Let's say this W is like 10,000. And let's say we have 3 tasks, A, B, and C. Let's say A has 100 lottery tickets, B has 50 lottery tickets, and C has 250 lottery tickets. So according to the lottery scheduling, C has the highest priority because it has more lottery tickets. Now, if I define the stride for A becomes 100, which is 10,000 divided by 100, which is 100. The stride of B becomes 10,000 divided by 50, which is 200. And the stride of C is 40, which is 10,000 divided by 250. Now, you can see here that the stride is the reverse of the lottery, right? The more your priority is, the lower your stride is, which is C has the lowest stride, which is 40. Now, how are we going to use these strides? We're going to have this another variable called pass. This is a counter that we're going to keep per thread. Every time a thread runs on CPU, we increase the pass by the stride of that thread. So everybody starts with pass equals 0. Then every time I run the lottery, if you get the lottery, so I actually don't run the lottery. Excuse me. I look at the pass. I always pick the thread with the lowest pass. Now, initially, all of them are equal, so all of them are 0. So I pick randomly. Let's say I pick A, and A runs. Now, after A runs, so I don't have a example. So let me run an example here with the previous example. So A's stride was 100, B's stride was 200, and C's stride was what was it? It was 40. So C's stride is 40. Now let's look at pass. So pass for A initially is 0. Pass for B is initially 0. Pass for C is initially 0. Now I look at pass, all of them are 0. So I randomly choose. Let's say we choose randomly A. Now A runs for one-time quantum. After that, I increase pass of A with its stride. So pass of A changes to 100. I add the stride of A to its pass. Now I have 100, 0, 0. Again, I want to pick the lowest pass. Now B and C have equal, so I randomly choose between them. Let's say I pick B and I run B. After I run B, I increase B's pass by its stride. So B pass of B becomes 200. Now, this time I'm gonna again look at 3 passes, 0, 100, and 200. Now I'm gonna pick the lowest one. Which one is the lowest? Well, C has the lowest pass, so I'm gonna pick C, and C is gonna run. After C is done, pass of C becomes 40. Now I have 3 numbers. Which one is the lowest? C has the lowest pass, so I'm gonna pick C again, and C is gonna run again. So it runs another one, and its pass becomes 80. Now, again, I'm gonna pick the lowest pass. Again, it's gonna be C, because C has the lowest pass. It's 40, so C gets to run. So C runs, and now C's pass becomes 120. So far, C has run 4 times, B has run 1 time, and A has run 1 time. Now at this time, I look at the passes. Pass of A is 100, pass of B is 200, and pass of C is 120. Which one has the lowest? Obviously A. So I run A. So now pass of A becomes 200. Now I have 200, 200, 120. Which one should I run? Obviously, I have to run C. So C becomes 160. And then it becomes 200. So now in total, I have run C for 6 times, A for 1 time, and A for 2 times, and B for 1 time. So at this point, everybody again has equal pass. So everybody became 200. Now look at this. I ran C 6 times, B 1 time, and A 2 times. Let's see if these numbers have anything to do with the number of tokens or the number of lotteries that each one of them has. So let me go back. So if you remember, look at these numbers. So C, I ran it 6 times, B, I ran it 1 time, and A, I ran it 2 times. Now you can see off the bat that A and B, the ratio between these two are exact same ratio between these two. And the ratio between these two, am I correct in 6, or did I run it 5 times? 1, 2, 3, 4, 5. Sorry, 5. Excuse me. So it's 5. Right. And then if you look at these two, 50 and 250, the ratio is 5, which is correct. And the ratio between 100 and 250 is the same ratio between 2 and 5. So in what we did with the stride scheduling is it's kind of like less randomness, but at the same time, we were able to stick to these, giving each thread its fair share of time on the CPU. And if you run it again, the same thing is going to happen. So in the next few rounds, you're going to run B for 1 time, you're going to run A 2 times, and you're going to run C 5 times. And again, they will have equal pass, and then you're going to repeat this. So all the time, you're keeping this 5-1-2 ratio between their execution times. So that's a stride scheduling. Now let me remove everything. So that was the 7th scheduling policy I introduced. So the 6th one was lottery scheduling. The 7th one was a stride scheduling. Now the 8th scheduling policy I'm introducing is max mean fairness. Now max mean fairness is very similar to this stride scheduling. So in a stride scheduling, we were doing max mean, meaning that I was always picking the minimum pass and I was giving the minimum pass CPU time. Now, with max mean fairness, we sort of do the same thing. So we keep track of how many times each thread has a run on the CPU, and we pick the thread that has run the minimum and give CPU to that one. So basically, at every round, I'm going to just look at how much CPU time each thread has gotten in the past. And the one with the lowest CPU time, it's going to run next. So this way, we make sure that everybody gets an equal share of CPU, right? If I always pick the one with the lowest CPU time, give it another time quantum, and then repeat this, I will make sure that, you know, after, let's say, n time steps, or sorry, after t time steps, everybody sort of has gotten the same amount of time on the CPU. So this is called max mean fairness. Now, this is fine. It kind of schedules the CPU equally between everyone. This begs a question of, what if I didn't want to give everybody equal time? What if one of these threads were more important to me, right? What if threads had different priorities? Then what you can have is a notion of right, let me. Okay, so before actually I talk about the when you have different priorities, let's look at it in action. Let's look at max mean fairness in action. If you want exact max mean fairness, meaning that you really want to equalize the CPU time for all threads, that's going to have high overhead because you know, you kind of, let's say initially everybody has 0, then you run one instruction of thread 1, then all of a sudden thread 1 is above of everybody else. Now for next instruction you have to go to thread 2, and now all of a sudden, you know, thread 1 and 2 have gotten CPU and everybody hasn't, so you have to go and execute the next instruction of the first instruction of thread 3. So this requires a lot of context switching to make sure that everybody really has gotten the same amount of time on the CPU. Now, this is too much, so we don't want to do that. This requires a lot of context switching in basically every instruction. You have to run one instruction of everyone and then go back and run every one instruction of everybody again, and so on and so forth. So it's kind of like round robin with time quantum of one cycle. So that's not good. So instead, we can approximate that. We can have a time quantum. Instead of just running one instruction, I can run a thread for one time quantum. And at the end of that time quantum, I look at everybody and see who has gotten the least, and I give it to them. For example, you might have a situation like this. So this is, let's say, at the end of time quantum. I look and I see that T2 has gotten the least. So I give T2 a time quantum. So it ran for a complete time quantum. And at the end of it, I do it again. Again, I look. Now, again, T2 has the least. So I give it again to T2. T2 runs. And now at this point, T3 has become the lowest. So next time quantum, I give it to T3 and I run T3. So this is kind of approximate max min fairness, because we're not making sure that at any given time these are all equal. So there might be a little bit off, right? But we're keeping them sort of at the same level by just going back and forth between the threads. Right. So this is how you can practically implement max min fairness. Now after this, okay, we talked about approximate max min fairness. Next is what if these threads have different weights? What if thread 1, thread 2, and thread 3 are not equal? Then what? So this brings us to the weighted max min fair scheduling. So with weighted max min fair scheduling, we're gonna consider everybody's weight in their allocations. So how do we do that? So we're gonna divide the time that each thread has gone on CPU by its weight. So instead of just looking at everybody's actual time on CPU, I'm going to look at everybody's virtual time on CPU. How do I define virtual time? So I'm going to introduce two concepts for weighted max min fairness. The first one is the amount of time that each thread is going to get is going to be the amount of time that each thread is going to get on CPU depends on how many threads I have and what is the sum of weights in my system. So I'm going to, let's say if you have, so this one is basically the max min fairness without weights. So let's say everybody had equal weight. Then the time quantum was simply, okay, I sort of messed it up. I so wanted to talk about weighted max min fairness, so I jumped. Let me go back and finish approximate max min fairness, and then I'll come back and talk about weighted max min fairness. So let me go back to this. So after we talked about approximate max min fairness, now what is an issue with this? The issue with this is if you have a lot of tasks, right? Let's say I have 100 tasks. So I have T1, T2, blah, 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 to T100. Now, let's say my time quantum is 1 microsecond. How it's going to happen? So I'm going to give 1 microsecond to T1, and then I'm going to look and give it to the next person with the lowest. Let's say I randomize between these two, between the rest of them, and I give it to this one. And then I randomize between the remaining ones, and I give it to someone. And then I again randomize and give it to someone. So I keep doing this until everybody among this 100 gets 1 time quantum. Now everybody is equal. So then I go to the next step. Then again, I pick randomly someone, I give it 1 time quantum. And then I pick someone else, I give it 1 time quantum. I pick someone else, I give it 1 time quantum. And this again happens 100 times until everybody is equal. And again, now that everybody is equal, then I can go 3rd round. So this happens again and again and again. Now, if I have 100 tasks and my time quantum is 1 millisecond, then everybody is going to get 1 millisecond divided by 100 milliseconds. So this is kind of how much time, what's the percentage of time on CPU. So everybody is going to get 1% of CPU. And if any of these tasks are, you know, let's say they require a response right away. Like, let's say you have moved your mouse or you have pressed the key and you want a response immediately, you're not going to get it, right? You're going to, worst case, you're going to wait for 100 milliseconds to get the CPU. Now, to solve this problem, we could reduce the time quantum based on how many tasks we have. So the more tasks we have, we can make the time quantum shorter to make sure that irrespective of how many tasks we have in the system, each task gets to run once every some number of microseconds, right? In this one, in this example that I have here, if I have 100 tasks and my time quantum is 1 millisecond, then my task gets to run one time every 100 milliseconds. If I have 200 tasks, then my task gets to run one time every 200 milliseconds. If I have 300 tasks, my task gets to run on CPU every 300 milliseconds. So it depends on how many tasks I have in the system. To get rid of this, I can make my time quantum shorter as I have more tasks. So let's say I can say that there is a target latency that I want to have. So this means that this target latency means every this amount of time, I want to run my thread at least once. So for example, you can say my target latency is 20 milliseconds. I want to run at least once every 20 milliseconds. Now, if I have 100 tasks in the system, then I do 2 milliseconds divided by 100. This becomes my time quantum. If I have 5 tasks in the system, I do 200 milliseconds divided by 5. This becomes my time quantum. So I shorten my time quantum as I have more tasks. That way, I make sure that every 20 milliseconds, my task gets to run at least once. So for example, here with 4 threads, the time quantum becomes 5 milliseconds. Now, what is the problem with this one? Now, this is fine, but what if you have so many threads? If you have so many threads, then your time quantum could become really small, because you're dividing this 20 millisecond by 200. And this is really small. Now, what's the problem with having a small time quantum? You should remember this from round robin. If you have really small time quantum, then you're going to have a lot of context switches. And a lot of context switches means a lot of overhead. So we're going to have to pay a lot of overhead. Now, let's say your context switching overhead is some number of nanoseconds. Let's say it's 3 nanoseconds. This already is 100 nanoseconds, right? If your overhead was 30 nanoseconds, then 1/3 of your time quantum you're going to pay the cost of context switching. So that's too much. So what happens in a real system, if you really want to implement this in real system, you can put a cap on how small this could become. So you, instead of saying that your time quantum is target latency divided by n, you can say your target latency equals maximum of really a small time quantum, like 1 millisecond, and then target divided by number of tasks. So let's say if target was 20 millisecond, and this number was 10, then this guy is 2, so you're going to pick between 1 and 2, you pick 2. But if you have 100, then this number becomes less than 1 microsecond, then you pick 1 millisecond. So this makes sure that your target, time quantum doesn't go below, sorry, this is not target. So this is quantum, time quantum. So this makes sure that your time quantum is not going to get really small. So you're going to cut it at some point. And this is what Linux scheduler does. So in Linux scheduler, you have a time quantum, but then it's not going to go below a certain number. So even if you increase the number of tasks in the system, at some point it's going to cut it up. It's not going to allow you to go lower than a certain number. Okay, now eventually I can talk about adding weights. So let's look at our journey so far. We talked about max mean fairness. Everybody had equal. Then we talked about approximate max mean fairness, where we use time quantum instead of being exact. Then we talked about changing the time quantum as we have more or less tasks. So that was the third iteration on max mean. Now the fourth iteration on max mean is what if tasks have different priorities? Right, what do we do? So the key idea is, so this is right now, this is the third iteration where we change the time quantum based on the number of tasks we have. Now, if tasks have different weights, then we can give everybody different time quantum. So when a thread with higher priority runs, it gets to run for longer time. If a thread with low priority runs, it runs for a shorter amount of time. Now, how much shorter or how much longer? It depends on their weights. So let's say if everybody had equal weight, if Wi was equal to 1 for all I, then this one would become exactly like this, because the sum over all of this would become n, and this is 1. So everybody would get target latency divided by n. So what we saw previously is a subclass of this more general scheduling with weights, because if everybody has similar weights, we're back to what we have discussed so far. But if people have different weights, then Qi, how much time thread I runs, divided by Qj, how much time thread J runs, you can see that this equals to Wi divided by Wj. Because this sum goes away, both of them have it, so it cancels out. Target latency goes away, both of them have it, so it ends up being this. So we're going to give, let's say if Wi is equal to 2 and Wj equals to 1, this means that the time quantum of thread I is going to be twice as big as the time quantum of thread J, right? Now, is this enough? Is this enough to have different time quantum for different quanta for different threads based on their weights? Is this enough? And the answer is no, that's not enough. We need one more thing to do, because, you know, if I'm still looking at how much time each thread has run, then I might make mistake. I might make bad decisions, right? So let's say I have thread A and thread B, and thread A has weight 2 and thread B has weight 1. Now, when A runs, A is gonna run for two time quantum, and when B runs, B is gonna run for one time quantum. Now at the end, let's say A ran and then B ran. Now I want to pick the next one. If I just look at how much they ran, I might pick I might pick B, because B just ran for one time quantum, whereas A ran for two time quantum. But so if I look at the exact time on CPU that each one of them got, I might make a mistake and pick B again to run. To avoid this, I'm going to introduce a notion called virtual runtime. Instead of actual runtime, which was how much time they ran on the CPU, I'm going to look at virtual time that they ran. And what is a virtual time? It's basically the actual time divided by the wait. So let's run an example, actually. I think the best way to understand this is to run an example. So let's go to this example. So let's say I have two threads, and let's say my target latency is 20 millisecond. And let's say the weight of A is 1 and the weight of B is 4. So what's going to happen is I'm going to have Q of A is equal to the weight of A, which is 1, times the target latency, which is 20, divided by sum of weights. So 1 plus 4, that's 5. So time quantum of A becomes 4 milliseconds. What about B? B's weight is 4 times 20 divided by 5. So this is 16. So time quantum of B is 16 milliseconds. Time quantum of A is 4 milliseconds. So let's continue. How are we going to do now? We're going to introduce this virtual time, which is going to be actual time divided by WI. So virtual time of I is actual time of I divided by WI. Now let's run this. So initially everybody, so V of A is equal, this is virtual time of A is equal to 0, virtual time of B is equal to 0. Now, just to remind ourselves, Q of A was 4 milliseconds, Q of B was 16 milliseconds. Now, very similar to the past, I'm going to pick the one with the lowest virtual time. So at this point, both of them have equal virtual time. So let's say I pick randomly, and let's say randomly I pick A. So A runs. For how long it runs? It's going to run for 4 microseconds. So then actual time of A, let's say actual time of A is going to be 4 milliseconds, and virtual time of A is going to be actual time divided by weight of A. Weight of A, if you remember, weight of A is 1, weight of B was 4. So virtual time of A becomes 4 milliseconds because the weight of A is 1. Now I have to choose between 4 and 0. Well, I will choose 0. So B is going to run. For how long? It's going to run for 16 milliseconds. So then actual time of B on CPU becomes 16 milliseconds. So I'm going to run B for 16 milliseconds. What's going to be the virtual time of B? The virtual time of B is going to be actual time divided by the weight. So 16 millisecond divided by 4, it's going to be 4 millisecond. Now I have equal virtual times. I have equal virtual times. But if I look at actual times, I can see that A got 4 and B got 16. And this is actually what I wanted. I wanted A to get 1/4 of B. And that's what exactly happened. Now, again, virtual times are equal. So I can randomly choose one of them. Let's say this time I pick B and B runs. B's actual time becomes another 16. So 16 before plus 16, that's 32. So V of B is 32 divided by 4. That's 8 microsecond. So now B's time is 8. A's time is 4. So I pick A. How long A runs? A is going to run for 4 microsecond. So then actual time of A, it was 4 plus 4. That's 8 microsecond. So now virtual time of A is 8 microsecond. So I'm keeping these virtual times equal, but in actuality, B is getting 4 times more CPU time than A. And that's precisely what I wanted. So I'm doing max min on virtual time. And by having these different time quantums, I get to implement this, this proportional allocation of CPU between A and B, which is exactly what I wanted. This one is very similar to stride scheduling. The concepts are very similar. So if you remember, in stride scheduling, we were doing this big number divided by the number of tokens, that the number of lotteries that you had, where the number of lotteries was basically your weight. So I was adding that to your weight. In a stride scheduling, the time quantum was equal. So I had equal time quantum. In max min fairness, I have different time quantum, right? So that's the big difference. In stride scheduling, the time quantum is fixed, for everyone. In weighted max min fairness, I have different time quantum for different threads, depending on their weights. In stride scheduling, I keep passes equal as I go. So I always pick the thread with the lowest pass. In weighted max min fairness, I pick the thread with the minimum virtual time. Okay, let me delete everything. Yeah, so this basically shows you what I just said. So the actual time of B and actual time of A translate to virtual time that is like this, right? So I'm just dividing by the weights here. This number actually should be both of them 4, not 1. So I divide 4 divided by 1, that's 4, as 16 divided by 4, that's 4. Okay. Now that's it. So I'm not going to talk about any other uniprocessor scheduling anymore. So I think that's enough. We talked about 8 different scheduling policies, and the last one had different iterations. If you followed. Now, how can we evaluate these scheduling policies? Now, one thing we could do, we can just create deterministic models, like pick a workload and model everything mathematically and do a mathematical analysis of which one is better. Calculate for your workload, calculate the the average response time, calculate your unfairness or fairness, whatever is suitable for your case, and do a deterministic modeling of your system. And this would be okay if you know your workloads, nothing is random in your system, then you can do this. In reality, we have a lot of randomness in our system, so we can't create these deterministic models. Even our workloads have randomness. So it's really hard to do this first one in general systems. One alternative to that is to create these stochastic models. Like, what does this mean? It means that you assume, for example, that there are some distributions in execution times, in certain events. You make assumptions that, you know, certain events follow certain distributions. Now, with that, you can now create this random and stochastic models instead of deterministic models. And queuing theory is usually the to go in these cases. We'll hopefully, if we get a chance, talk about queuing theory and how it could come handy in analyzing stochastic models. But even this might be too much for your system. Maybe, you know, you don't know the distribution of events. Maybe the distribution changes, right? Maybe you can't, maybe, you know, the model is so complicated that even if you use these stochastic models, you can't really mathematically analyze your system. So in that case, so the first one fails, you can't do this. The second one, you can't do this. Your last chance is to actually implement this and simulate it, right? So if you don't want to, if your system is too complicated to be modeled or too deterministic, it's too random, and you don't have the parameters of your random distributions, then you can just simulate your system. And this is actually very common in many cases. Either the system is too complicated or we don't want to make any assumptions about the distributions. So our last chance is to just simulate the system. Just make it and simulate it. Now, one thing you have to be careful if you end up simulating your system is that you have to make sure that you're simulating the same things in your systems. Now, this actually hits home with me very recently with one of my graduate students. We were working on a scheduling policy, and we wanted to compare ourselves with other work in this area. Now, there was this other paper that we were looking at, and we figured that we can't beat them. Their numbers were so good for us to beat them. And it didn't make sense. Their numbers were too good to be true. And we were just, you know, scratching our head, what's going on? Why it feels like our system is better than them, but our numbers are worse than them? Basically comparing their numbers against our numbers. Turned out that the way they were simulating their system and the numbers that they were reporting were not inclusive. They were suffering from a starvation and sample bias. Let's dive into this, and then I'll come back to this example. What is a starvation and sample bias? So suppose that you want to compare two scheduling policies, a scheduling policy A and a scheduling policy B. One thing that you could do is you can create this infinite sequence of tasks that come to your system. And then you can have a start time. You can say, okay, I'm going to measure response time, for example, or I'm going to measure throughput, or I'm going to measure whatever you want to measure. And at some point, you might say, okay, stop. I ran my system for an hour, for 2 hours, for 1 day, for 1 week, whatever your time is. And now I'm going to look at my data. I have measured, response time of millions of tasks. Now I probably have a good idea of average response time. I can just sum them up and divide them by 1 million, and I get my average response time. Now, is this a good method? So, and by the way, this was what that paper was doing. So the paper that we were comparing and their numbers were so good, they were doing exactly like this. So they had a start time, they had a finish time, and they were reporting their performance. And it was really good. Now, is this good? Is this a reliable way of comparing performance policy A and scheduling policy A and scheduling policy B? The answer is no. Because let's say your policies are SGF and FCFS. Now you have an infinite number of tasks. And by the way, in that case, it was kind of the same. So we were doing FCFS, as a scheduling policy similar to FCFS. So first come, first serve. They were doing something that was close to SGF. They were doing something like, and this is like few months ago, actually. That's why it hits home. They were doing something like this multi-level fair queuing. So they were, prioritizing the short tasks. So they were running short tasks, and long tasks were pushed to lower queues. So what happens is, after an hour of execution, FCFS has executed task 1 to task, let's say, 1000 or whatever, based on their arrival. So the first one executed, the second one executed, the third one executed, and now I'm executing task number X. Whereas SGF has only executed the short tasks in this sequence, and the long tasks haven't been executed yet. So if you stop your execution after 1 hour and look at the response time, obviously SGF is better because it has only executed the short tasks. But what about the long tasks? So long tasks haven't even been touched. They haven't been even executed. Whereas FCFS has executed long and short tasks. So in essence, if you look at these numbers, you're comparing apples and oranges, because the set of threads that you have executed are not the same. So how can we change this? How can we make equal comparison? One method that we used and then turned out that we were beating the other system was this one. So instead of having a start time and a finish time, I can just look at certain number of tasks. Say I put number on each task. I say task 1 to task, every task that I create, I give it a number. And I can say I run this system until you finish task 1 to 100. Now, I don't care if you also finish some other tasks, but I want to make sure that you have finished task 1 to 100. And, FCFS takes some time to do 1 to 100. It's going to run the first one, then the second one, the third one, and so on and so forth. SGFS, however, is going to run maybe task 2, and then task 5, and then task 20, and then task something, and then may get a chance to go and run task 1, and then get a chance to run task 4, but then it could just go ahead with other tasks. So once both of them finish executing task 1 to 100, then I pause. So I could run FCFS for X amount of time, and that could be different for how long I run SGF to finish the same number of tasks or the same set of tasks. And once both of them finish the same set of tasks, then I look at their numbers for that set. So in this case, FCFS probably has just finished 1 to 100. SGF might have finished 1 to 100 plus some other tasks from 100 to maybe 1000, right? Some of those tasks. Now I throw away those results because I don't care about those from tasks that are not in this set. And I just focus on the tasks that are in this set. And now I can compare, for example, the average response time. So this is a method that you can use to take care of sample bias. But this method might not work with, if you wanted to measure throughput, right? Because SGF has maybe ran more tasks, maybe. I mean, it depends, right? So sometimes this works, sometimes it doesn't work. So you have to come up with creative ways to make sure that what you're comparing is fair. You're not comparing, oranges and apples. So this is one example. Now, just to finish, I know I'm over time and I didn't get to talk about multi-threaded scheduling. So this is just a summary of everything that we talked about. So if you care about throughput, usually FCFS is your choice because it has the least amount of context switching. If you care about average response time, then SRTF is your choice because it mathematically minimizes average response time. If you care about I/O throughput, if you remember that example that we had, your SRTF is probably the best you can do because, again, go back to that example and you'll see. If fairness is what you care about, then you can do max-min fairness, for example, or lottery scheduling, or this one is the Linux CFS. Linux CFS is basically the weighted max-min fairness. So they're very, very similar, like they're almost equal. So the Linux completely fair scheduler has some implementation details in terms of how threads are kept in the ready queue. It also has some real-time components to it, so it's not exactly weighted max-min fairness, but they're very, very similar. It's the similar concept that is implemented. Now, if you care about, how much time for your fairness, how much time each thread has gotten on CPU, round robin is your choice. If you want to favor tasks with higher priorities, then you might do a strict priority. If you care about proportional sharing, then lottery scheduling and stride scheduling might be your to-go. So with that, this is the summary of everything we talked about. And thank you for sticking around. Sorry I went over time. I got one question. So is weighted max-min fairness similar to stride scheduling in the sense that the task with the lowest calculated execution time, however that may be, is always run? Oh, sorry, never mind. You just answered that. But yeah, okay, good. Yeah, I really, if you go back, I compared weighted max-min fairness and stride scheduling. They're very similar in the concept. The only difference is in a stride scheduling, we have similar time quantum. In weighted max-min fairness, we have different time quantum. But then, in stride, we're looking at paths. In weighted max-min, we're looking at the virtual time. So those are the differences. Okay, thank you so much. Take care, be safe. Talk to you on Thursday. Bye-bye.